Good morning, ladies and gentlemen, and it's time to start this morning session. The first speaker in this session is Professor Siddhartha Mishra from ETH Zurich. His topic is AI for PDEs. Let's welcome.
So first of all, you can hear me, right? Loud and clear. Okay. So thank you very much for the kind introduction, and I also take the opportunity to thank the organizers for inviting me to this very interesting conference at this beautiful, beautiful venue. So without further ado, let me start. So let's see. So let me start with some examples when I'm talking about AI for PDEs, right? This is a big topic, particularly here in China, but still, it's nice to give a little bit of motivation. So let me take a problem that we have worked on for a long time, and the problem is in tsunami predictions. So this is the Mediterranean, but it could also be the Pacific Ocean along the coast of China. And just imagine that there's an earthquake here off the coast of Crete, and once there's an earthquake, the sea level rises or is deformed, so the water level also rises, and this sets off a tsunami wave. So now the agency, that is the Italian Institute of Oceanography, who are responsible for issuing tsunami warnings, what they have to do is that they have to make a forecast of certain locations along the Mediterranean coast. So here along the coast of Greece, here along the coast of Italy, and they have to make predictions like this. They have to calculate with respect to time how the wave height changes, right? So there's a measuring station, they will make these calculations, and if the wave height is at a certain level, they have to issue a tsunami evacuation warning. So this is a very typical problem in geophysics, that you have to make this kind of forecasts, right? The second problem that I have considered quite a lot is from engineering, not from science, but from engineering. And this is with a company called Dallara. Now, Dallara, you might not have known, but they are the main designers of race cars for Ferrari. And all of us know Ferrari, right? So this is an example of a race car that they designed for Ferrari. So this is a race car, and what they're interested in is how the aerodynamic properties of this race car change when you change the shape. For instance, they want to adjust the tail fin here, they want to adjust the front fin here, or some side fins, and they want to see how the drag changes, how the lift changes, and so on. And they want to have an aerodynamically perfect race car, right? Because then it will go even faster, it will win your Formula One competitions. So this is a typical problem in engineering where you have a complex shape and you have to make some predictions, some physical predictions about it. So now, how are these problems solved at the moment, right? How do we solve this? There are many experts in numerical analysis here, so the pipeline is very well known. So first, we need to have a mathematical model of these kind of physical systems, and typically these mathematical models are PDEs, partial differential equations. We all know that in some sense PDEs are the language of nature because they model everything that you can imagine, all the way from the subatomic particles, electrons. These are modeled by Schrodinger's equation, all the way to black holes or the collision of black holes, which is modeled by the Einstein equations, and everything in between. So a very, very different kind of physical phenomena, and at the same time also a whole range of scales, right? So just think in terms of spatial scales, this is 10 to the minus 18, this is 10 to the 18. So in between this, there are 36 orders of magnitude, right? So this is an enormous range of scales that PDEs model. But as many of us know, you cannot solve them by hand. You have a PDE or a system of PDEs, there's no way that you can solve them by hand. What we do is to use numerical methods. There are many experts here in the audience to do that. And there are different kinds of numerical methods: finite difference, finite volume, finite element, spectral method, a lot of them. And they're very, very successful, including from my laboratory, my lab. So for instance, we do simulations in astrophysics, in geophysics. So this is a simulation of a cloud, this is of a tsunami induced by a rock slide, this is flow past a rocket. This, I was in Beihang University yesterday, and they're very curious about these kind of calculations. And then some engineering applications, many different domains, many different examples, and there's a lot of success there. And particularly about the examples that I started out with. So for instance, to simulate a tsunami using the shallow water equations, you can use finite volume methods, you can use also finite element methods to simulate flow past a race car using some Reynolds average Navier-Stokes equations. So this is a very successful, very well established field. There's a lot of research activity going on, including here in China. But what is the catch, right? What's the issue that I'm going to address today? So the first point is that these simulations that I just presented, some of them can be very, very expensive. The computational cost is very high. Let me give you some example just to illustrate what I'm talking about. So this is an example. This is a simulation, a fluid dynamics simulation. So I want to solve the Navier-Stokes equations, something called direct numerical simulation. I want to simulate all the scales of the problem. So this is the initial condition. This is the solution, the vorticity of the solution at a later time. You can see it's a very, very complex solution. This is because I have simulated it at very high resolution, 1000 cubed. So 1 billion degrees of freedom at every time step. So this can only be done on a supercomputer. We have a code which is written on GPUs, and on our supercomputer in Switzerland, this takes about 100 GPU hours. Not so bad, right? 100 GPU hours. But the point is that this is a turbulent fluid flow. It's a chaotic system. If you make tiny, tiny changes in the initial conditions, you see that the solution changes dramatically, right? So to make one simulation doesn't make any sense because you make a tiny perturbation, it changes completely. So what you have to do in this case is something called uncertainty quantification. So you have to simulate many, many, many of these flows and then compute statistics, mean, variance, and so on. And to do that, you have to sample at least 1,000 of these simulations. And 94 is each simulation, 1,000 times 94 is 94,000. And then this is slightly more. This becomes much, much more expensive. In fact, how expensive? So on our supercomputer, this is $500,000. Of course, you have to write grants, but this is the number that we're talking about. So just imagine all the computation that is done using PDEs and how expensive it is. So this tells us that first of all, PDEs need to be solved fast, particularly when they have to be solved multiple times, like in design, inverse problems, uncertainty quantification, and so on. So that's the first issue, that you need to be fast. The second issue, which is as important, perhaps even more important, is that you can only solve a PDE if you can write it down, right? So if the system is already modeled, but in many, many problems, this is far from the case. Let me give you an example. So this is the Earth system, entire Earth system. To make weather predictions, particularly climate, we need to understand the entire Earth system and several parts of it. So this multi-physics, right? So the fluid flows in the atmosphere and the ocean. This is Navier-Stokes, some version of Navier-Stokes. Similarly, radiative transport, radiation from the sun, this is radiative transport equations. And these are well known, right? You can write down the equations, you can write down thermodynamics and so on. But the problem is there are processes here like forest, for instance. You see there's a lot of forest around here, there's a lot of forest all over the globe, and this you cannot write down a differential equation to, to sort of model it. Similarly, the role of land, soil, aerosols, there are many, many difficult processes which cannot be modeled from first principles. So whenever you talk about complex systems, subsurface flows, flows in the brain, traffic flows, and so on, it is very, very difficult to write down PDEs which describe them. What happens is you end up with what is called a sim to real gap. So people do the simulations as perfectly as they can, but when they make measurements of the system, they see that there is a gap here. This is because there are modeling errors. You cannot avoid this. So even if the numerical simulation is perfect, you'll still have errors, right? So there are two issues there. So either the PDEs are too slow to solve, so they need to be solved fast, or you don't even know them, right? So you need to do something about that. So these two issues, this is sort of the motivation for what I'm going to talk about, because in both these cases, what we have in addition to the physics is data, right? Particularly for the climate system, we have a lot of data. For many of these applications, we have a lot of data. The question that I'm asking, or the community is asking, is if you have data and you have your physical knowledge, can you combine these two so that you can solve PDs or physical systems, you can simulate them fast and you can simulate them more accurately by using or leveraging data. So this is what I'm going to do. But how do you do it? First, let's try to define the problem mathematically, right? So that we are clear about what we're talking about. So now you have a PDE. So I have written down two different PDEs here. So this is a standard elliptic PDE, something called the Darcy flow equation, or this models heat conduction inside a material of complex conductivity. And so you can see here that this is the forcing term. I can put it to 0 even if I want, but let's say that this is a given term. Now what I'm interested in is if I change the material properties, the conductivity of the material, how does the temperature change, right? So this is a typical solution operator because I take my input, which is going to be a function, which tells you the coefficient here, and my output, which is the solution of the PDE, and then I do the mapping between them. So this is your solution operator. Similarly, for a time dependent problem like the compressible Euler equations, so this is initial datum, density for instance, and this is the solution at a later time. Very complex, but this is where the flow has evolved, right? So again, the mapping takes the initial condition, which is a function, to the solution at a later time, or the trajectory of the solution at a later time, which is also a function. That's why we have operators here, because we have mappings which take functions to functions, so infinite dimensional mappings, right? That's why they are operators. So if you have access to the solution operator, then your PDE is solved, right? Because you can just put the input and it will churn out the output. So this is the object that I want to learn from data. So whenever I'm talking about learning a PDE, I'm not learning the form of the PDE, I'm learning the solution operator of the PDE. But now the question is, you have to model the data, because learning is with respect to data. It cannot be independent of data. So now you have to model the data. So I assume that the data comes from a probability distribution. Let's say on the inputs, this is going to be an infinite dimensional object, can be well defined, no problems with that. And now we are going to sample from it, or we assume that we have access to samples. So these are samples, as you can see here. I'm assuming that there is no noise in the measurements, but no noise can be added. That's not an issue. So now you have access to this information. You might or might not have access to the form of the PDE. That's not that important. And the objective or the task here is that I want to approximate what is called the push forward measure. So the action of the PDE solution operator on this data distribution. So it's a very clear, mathematically well defined learning task. But the point is that it's an intrinsically infinite dimensional task, because PDEs are the solution operators themselves are operators. So everything happens in infinite dimensions. So how am I going to learn this? Now, we all know the answer to some extent. This is the age of AI. So I'm going to use deep neural networks. But the moment I have to use deep neural networks, there's a problem. And the problem is the following. Neural networks, as you will see in the next slide, these are always mappings, whatever be their form, these are always mathematically defined as mappings which take a vector input and produce a vector output. Okay, so finite dimensional input, finite dimensional output. The input and output can be very, very large dimension. For instance, Zora, the image generator, actually I was in Shinhua University and they have an even better image generator. But it doesn't matter, because the output of this is like 32 million dimensions. Very, very large output. Nevertheless, it's a finite dimensional output. But what did I tell you? That for the problem that I have in hand, it's an infinite dimensional problem. My inputs and outputs are infinite dimensional. Here, my inputs and outputs are finite dimensional. So there is a dichotomy here, a gap. But this is precisely numerical analysis. In numerical analysis, we precisely address this problem, that we take something which is infinite dimensional, which is the structure of the PDE itself, and then project it into some suitable finite dimensional space. So this is, in some sense, a well-known problem in numerical analysis. But how do I address it then? So there are different ways. There's no unique way. There are different ways. Let me just try to motivate with one particular way. So what is the idea here? So neural networks, these are mappings, so deep neural networks, these are compositions of different elementary functions. But each elementary function here, or each layer, has a very particular structure to it. The structure is very simple. You give it as a vector as an input, then there's a matrix vector multiply. You add another vector. This is what is called the weight matrix. There's a bias vector. These are learned. These are learned from data. And then you apply a nonlinearity pointwise. So for every component of this vector, you apply the same nonlinearity. So that's a neural network. There are different structures that you can put in on this weight matrix on the bias vector, but at the end of the day, that's what it is. Now the idea is, why don't we generalize this construction to infinite dimensions? Now this is not my idea. It was proposed by some people in Caltech some years back, a few years back, and it led to what are called neural operators. So neural operators are just infinite dimensional extensions, natural, canonical, infinite dimensional extensions of neural networks. So the same layered structure is there as before, nothing changes. What changes is the structure of each layer, because remember that now my input is going to be a function and my output is going to be a function. So of course this vector has to be replaced by a function, direct replacement, no problems. Now all of us know that as long as you have done some elementary function analysis, that the infinite dimensional extension of a matrix vector multiply the canonical one is a kernel integral operator. So this is what we teach to our students, right? So this is a kernel integral operator. You take the function input, throw it against the kernel, and integrate. And then they suggested that the nonlinearity be applied again pointwise at every single point. So it's a very straightforward extension, right? Nothing fancy about this. Of course, there are some choices to be made. We need to choose the kernel, we need to choose the nonlinearity, and so on. And remember that this you can't evaluate on a computer, right? At the end of the day, we want to put it as an algorithm. This cannot be algorithmized. It has to be discretized because, as always, means you can't evaluate integrals just like that. So we need to discretize it in some form. So you need to make choices. One choice, which is heavily used in the community, is based on the same group, but they did it a little bit before. It's called Fourier neural operators. And the idea is that you take this kernel. Physics is about translation invariance. A lot of the physics that we see is about translation invariance. So you make a translation invariant kernel, then this becomes a convolution. And one way to evaluate convolutions efficiently is to use Fourier transforms, is to do it in Fourier space because it becomes a Fourier multiplier, right? So you start with a function, discretize it, of course, take a discrete Fourier transform. You can do it log linear with FFT, as we know very well. Then you have a learnable Fourier matrix, a learnable Fourier multiplier, inverse Fourier transform, come back to physical space, apply the nonlinearity pointwise. It's a very, very simple, straightforward construction. Has the advantage that you will have efficient implementation because of the FFT, at least on Cartesian grid. So what is the idea here? That we do convolutions non-locally because of Fourier representation, but the activation function, the nonlinearity here, is local. So this is a very, very well established. There's some solid theory behind it, including my lab. But this is one choice, right? But this is not the unique choice to do this. Another choice, which I like more, because I'll tell you in a second why that is the case. This is from us some years ago, a couple of years ago, is to do the same thing, but now in physical space. No more Fourier representation for the convolution. The convolution is still local in physical space. Convolution kernels are compactly supported, so this is an efficient operation. But the interesting point is that we do the nonlinearity non-locally with some Fourier representation. So this is somehow inverting. And the reason is there are many people doing numerical analysis here, so it's easy to explain, is that whenever you take a function, just imagine the orange function, right? So you take a function, you apply pointwise nonlinearity to it, like ReLU, this is just a positive part of the function. In physical space, everything is good, right? So this is the blue curve here. But in Fourier space, things are bad. Why? Because whenever you take a function with a finite number of frequencies, apply a nonlinearity, you like, so if you have sine 10x and you square it, you get sine 20x, right? Because nonlinearities, they increase your band limits. So what happens is that even though your original signal has certain finite bandwidth, the new signal, after you apply the nonlinearity, this has these higher frequencies, which might or might not be visible. And this leads to what is very common in spectral methods called aliasing. And as you'll see later, this is going to be a problem. So in order to tackle this problem, what we do is that we don't apply the nonlinearity pointwise. We first sort of upsample and then sort of cut the nonlinearity to reduce or in fact eliminate this particular aliasing. So remember that there are two choices here, at least two choices. Either you do the convolution in Fourier space non-local, activation local, or you do the convolution local and activation is non-local. The other things are just details. That's not important. So what happens? Let's try to test these two ideas out, right? It's a very simple test case, just two-dimensional Navier-Stokes on a Cartesian grid. So this is your operator, initial conditions to a later time. In vorticity, you can see that this leads to certain vortices, and both the methods do quite well, CNO and FNO. But you can see that here there is some artifacts, and these artifacts are due to this aliasing that I just mentioned. High frequencies come in which shouldn't be there, right? So now the consequence of this is very deep. The consequence is the following. Remember, I told you that we are doing some discretizations. We are trying to learn some things on a discretized level. So of course, while training my neural networks or neural operator in this particular case, I fix a resolution. This is 64 square, just for simplicity. But during testing, when I deploy my neural operator, I can test it at any resolution, right? This is otherwise it will not be an operator anymore. But when I tested at different resolutions with this Fourier neural operator, because of aliasing, you see that the error, it increases here slightly, but here more heavily. Some others it increases dramatically. But with this new construction that I did, local convolutions and non-local nonlinearities, you see that it's flat. This is because we can prove a theorem which says that there is no aliasing error, and because of that, this is it will seamlessly generalize across grids. So there is some mathematical advantage to doing that, and you don't lose anything because the error is anyway lower in this particular case. So this is because I don't have that. Right? This is because there is a commutative diagram. Because remember that what I did with the neural operator is that I first learned something at an infinite dimensional level and then discretized it, right? But you could do the opposite. You could discretize and then learn, and if these two things don't commute, then you'll end up with these kind of errors. So by having some structure preserving property, we are able to get rid of them. So this is one example of this. But this is not the only thing, right? You can choose whatever kernels you want to choose. Means so far we chose linear kernels, right? So I said that my kernel is linear, learnable but linear. You can make it non-linear. Nothing stops us from doing that. And there is one particular choice. The details are not important here, which leads to what is called attention. Now, all of us use ChatGPT or DeepSeek or whatever. Now, all these objects, these are transformers, and they are based on an operation or a mathematical construction called attention. And this is a representation of attention is nothing but applying a nonlinear kernel like this and then discretizing it. Okay, that's attention. But this kernel, of course, looks complicated, but actually it's very simple because you can understand it from this diagram here. So remember that I want to update the value of this point here or accumulate information at that point. So if in a kernel method, I just take information from all the points and then update it, but I have to weigh them, right? So the weighing is what the kernel does. But now the weights, these guys here, they are decided based on another round of correlations. Okay, so we somehow calculate the correlations, then decide the weight and the update. So you have two all-in-one calls, which is very good because you have some global information exchange, right? Each point knows how important it is contribution to the other point. The problem, of course, as you can imagine, is that this is going to be quadratic in the number of points. So once it's quadratic for language, it's okay, because when I'm talking in English or Chinese, you can just tokenize it or represent it in some small vector, but for the 3D sort of solution field of the PDE, this is just too expensive. So you cannot do that. We have to come up with some representation which is different. Thankfully for us, people doing image computer vision, they have some ideas which can be readily adapted to our case. And these are, for numerical analysts, these are sort of straightforward extensions. Why? Because instead of applying this attention operation, this kernel, to each point value, this is going to be very expensive. What I can do is I can take my domain, I can divide it into cells or blocks. These are these white blocks that you can see, cells. And just like the finite volume method, I don't apply everything to a point value, but to a cell average, right? So this is a finite volume method. This can be done. No problems with that, and this will help me scale things much better. However, the problem is that it depends on the cell size. If the cell size is small, then the computational cost is large, but it's more accurate if the cell size is large, then it's not accurate and so on. But there's another trick which actually comes from Microsoft research in Beijing for images. It's not for scientific applications, but we can readily adapt it. So what they suggested is what we call a two-level discretization, in finite elements, for instance. So you come up with two discretizations, the white one, which is my cells, and the black one, bigger boxes. They call it as windows. Okay, let's say that these are windows, and the idea is that you localize. You don't use this global information. You only put attention across all the points in this window. Only put attention across all the points in this window. So then everything, the scaling is much better, right? It's not a global operation anymore. It's a local operation in some sense. But then what is the global information transfer? Here is the trick. So remember that I have these layers, one on top of the other, one on top of the other. So in the next layer, what you have to do is just shift the windows, So these points which are not talking to each other in one layer, they're talking to each other in the next layer. and then you iteratively do this. This is very similar to domain decomposition methods. They didn't know about this, right? But we know, and we can adapt it to our scientific applications. So this is the version of transformers that is currently state of the art for scientific applications. It's called SWIN transformer or Scott scalable operator transformer. Again, the details are not important because in machine learning there are lots of sort of small details. You have to put some residual blocks and so on. But the basic idea is either to use convolution or attention and to do it in a multi-scale manner. So that's the basic construction. So you can use convolutions, you can use attention, linear kernels, non-linear kernels. There doesn't seem to be a big difference between them. In some problems, one is better. Like here, for instance, Scott, the attention-based thing is better. Here, the convolution one is better. So there doesn't seem to be a particular, let's say, advantage of one over the other. But the bottom line is that if you are in 2D on a Cartesian grid, because whatever I told you was completely on a Cartesian grid, then there is no issue in some sense. Machine learning today is very, very accurate, as you can see across a whole set of problems here. And the errors are always 1-2%. So this is all that you need, right? You don't need, for most applications, better errors. But this already tells you what the limitations are, because Cartesian grid 2D. So I already made quite some strong assumptions. So now, but we all know that in engineering in particular, it's not. So this is the problem to some extent is solved now, right? But what really we need to do is to have grids like this, right? Very complex geometries, foil for instance. And on the car, I don't know if you can see this, but there is actually a mesh on the car, lots and lots of different points. So finite elements have been designed to do this. Can we sort of learn that, right? So this is more of a challenge, but there are ways to do so. One way which many people use is to use graphs. So why graphs? Because to have complex point distributions like this one or this one, you can always represent them as a graph. There's always some connectivity, there's some information and so on. And it turns out that neural networks can process data on graphs, right? So this is what are called graph neural networks. And it's very, very simple. Function is very simple. Let me represent it visually, pictorially. So now just imagine that I want to update my whatever node temperature or pressure at this particular point on my graph. Then what I do is I look at my neighboring points, okay, and then accumulate information. These are called messages. This is a multi-layer perceptron. These are called messages. Accumulate information, add them up usually, and then process them by a nonlinearity. So it's a very, very simple construction. You can also represent it as like a matrix vector multiply, but it's essentially a very simple construction, and this will give you a graph neural network. And in principle, we can adapt it to the situations that we have, very complex grids and so on. So this is more or less state of the art. It's from my lab now. It's just a couple of months old. So what you do is you do this graph neural networks, but you do them in a multi-scale manner, because remember that physics is all about multi-scale information processing. So we do a lot of message passing, but we do it in a multi-scale manner. And this gives us a neural operator which can work with very, very arbitrary data structures. So what are the advantages of this? So you can handle complex shapes, like a circle is a very simple shape, but you can also handle airfoils, you can handle some complex domains in elasticity. All this can be done, no problems. It's very accurate. I have a bunch of here, but essentially the point is that this can be made very accurate. Errors are sometimes it's 5-6%, but this is it depends a little bit on the data. But essentially you have very accurate solution of this very complex domains problem, but there is a catch, and that's why I'm not spending too much of time. We are very happy with the results, but it's not efficient at all. Even in 2D, to do some of these calculations, it took us a day or two to train this on a GPU, and this is very expensive. It's computationally very expensive, and the reason is anyone with some basic knowledge of computer science can understand it. Is that graphs are a very sparse data structure. So information has to be collected. There's only so few neighbors per node, right? So if your graphs are different during in each batch, as it's called, then you have to do a lot of repeated memory, sparse memory accesses. And for modern GPUs, this is not optimal at all. So it's very, very slow. It's difficult to scale it beyond a certain number. So what's the solution? The solution, one of the solutions at least, is from a very bright Chinese student of mine, Shazhang Ban. What he came up with, what we came up with, is to combine graphs and transformers. I just explained transformers. So what do we do is something very interesting. So you start with a grid or a point distribution. I don't know how well you see it, but you see the blue points. This is the airfoil grid, right? So this is the airfoil grid. So it's a lot of points around the shock waves, very few points otherwise. So what we do is we want to transfer information on this very complex point distribution to essentially a Cartesian grid. It need not be a Cartesian grid, but for simplicity, to a Cartesian grid. And we do this part of the information transfer, what is called an encoding, by using graphs, multi-scale graphs. Multi-scale is the key point, because without multi-scale, you cannot get these results. And then once you are on a Cartesian grid, so you do a transfer. Once you are on a Cartesian grid, you can use transformers using attention and so on that I just described. We use a vision transformer or a swing transformer. And then you want to come back, again you do some multi-scale information deaggregation or decoding to your original grid. So start with a graph, transfer information, use transformers, come back. There are many other tricks, but this is essentially the idea. And the advantage of this, you'll see, is that first of all, it's as accurate. It's not more accurate than a graph-based method. It's comparable accuracy, but it's much more efficient. How much more efficient means it's like whatever used to take more than a day takes half an hour or less. So now this is the architecture that we can take to 3D, because that's the challenge, right? You want to do complex grids, you want to do 3D, because without that you can't do engineering. Can we do that? The answer is yes. I'll give you some examples. So this is an example. It's from MIT, the data set. It's called DriverNet++. So what the people at MIT did is that they took 8,000 different car shapes, passenger cars, not race cars, 8,000 different car shapes, and then they did some RANS simulations, and they computed surface pressure, stress, and so on and so forth. And the task is, take this, make a machine learning model work on it, and then test it for new car shapes so that you get reasonable error. So the main challenge here is twofold. First of all, there are 8,000 cars, so you have to do quite a bit of compute. And second, on each of these cars, or at least on the surface, you have 2 million surface nodes already. So if you do a graph-based method, you have to work with 2 million nodes and about 15 to 20 million edges, which is quite a big graph. Difficult for a graph neural network to handle this, but with our architecture, it's called GOAT. This is no problem whatsoever. This entire thing took less than a day to train it in 3D. It took less than a day, and the results, because we have this highly expressive architecture, the results are very good. We are state of the art on this data set at the moment, and it is significant error, because we are able to combine a very powerful architecture with the ability to scale, so that we can actually compute on all these car shapes. So you can do 3D. In fact, you can do more than that, because in the meanwhile, people at NVIDIA, they released a different simulation, similar kind of cars, but they replaced the runs here, which was the previous data set, with LES. Now LES is much more accurate, which means that on the surface you have more than 10 million nodes. On the volume you have 50 million, but on the surface alone you have more than 10 million nodes. So now your architecture really is tested, because it has to scale with respect to that. Again, no problems whatsoever. We were able to do it again in a day. This is only 500 cars, so it's not so much of data, but the errors are very small. You can really calculate that. So this is quite satisfactory, and we can actually do a full aircraft now. So no problem with that. You take a full aircraft. There is some effort from AIAA. So you take an aircraft shape, and then you compute things like the pressure. You compute things like the skin friction coefficient and so on. Again, the challenge is about complex shapes, complex geometry, little amount of data. So you need to scale, and our architecture is able to do that very well. So essentially, we can do 3D simulations at scale, no problems. And this is very recent. The paper is only a couple of months, less than a month old. So that's good, right? So you can do complex 3D domains, and you can sort of run machine learning on it. But what's the challenge? The point is, once you go to 3D, things get more complicated, right? So let me show you what the challenge is. So that let me just have a look at time, so that I'm not totally out of time. I am how much of time? So I started at 40. Okay, so I'll hurry up a little bit. So now let's take up the ante a little bit. So now what you're seeing here is a standard fluid dynamics problem, Taylor-Green vortex, 3D, solved with the spectral method, direct numerical simulation. So what you see here are three plots, right? So these three plots, so you take the initial condition for the Taylor-Green vortex, you make tiny little changes, and then you get these three tiny changes, and you get these things, right? So first of all, you see that there is a lot of small scale information. There's a lot of small scales that are happening. Second, what is happening is it's a chaotic system. So if you concentrate on any region, you see that there is a lot of variation within the samples, right? So these are the two things that are happening. So there is small scales, there's variance, there's sensitivity to initial conditions, sensitivity to conditions. Now I use whatever machine learning model, including my own, the nicest machine learning model that I've talked to you about, and this is what you get, you know. So all the small scales are gone, right? There's no small scale information anymore, and there's no variance. There's a lot of variance in the ground truth. There is no variance here. So what's going on? So actually this can be very nicely mathematically explained in 2 lines, and let me try to do that. So it's based on a hypothesis that is very reasonable. The neural networks, the way we train neural networks is by using gradient descent. So gradient descent means you move in the direction of the steepest gradient. So the gradients have to be well behaved. If the gradients are unbounded or the gradients are tiny, then it doesn't make any sense. There will be no steps. Gradients have to be well behaved. What does it mean? So gradients are well behaved means that essentially the Lipschitz constant is going to be bounded, right? It's of the order of 1. If the Lipschitz constant is of the order of 1, then what happens is that your neural network is not very sensitive to small perturbations. So you have this system here. So you take a tiny perturbation, you don't see a huge change, right? So this is, you cannot avoid, this has to be done, otherwise the neural network cannot be trained, okay? So once you do that, then you can explain what's going on. Because remember, my map that I'm trying to approximate, this is very sensitive to conditions. So even if I make a small change here, this doesn't mean that it collapses to this value. My neural network, on the other hand, because of this training, it's called edge of chaos in statistical physics, this changes and this sort of gets back to this value here, because this is insensitive. This guy is sensitive. Now I break this into 2 parts, right? It's straightforward decomposition. One part you can see here is essentially the variance of my ground truth with respect to the small perturbations. So this is a large quantity and it's independent of your neural network parameters. So whatever you do, this term will be non-zero and it can be large. So you cannot train a neural network to optimization in this particular case. Second, what is happening is that this term here, it's a positive term, so you can make it 0 at best, right? And how do you make it 0? You set this value to be the mean value of the perturbations. So what does this mathematical analysis tell us is that if you have a chaotic system that you're trying to approximate, then the neural network will always regress or collapse to the mean. And sorry, this is what is going on, right? So there's a clear mathematical explanation of what is observed empirically. But so is there any hope here? Because after all, there are many PDEs which have chaotic solutions, right? So we need to approximate them. It turns out that there is hope, provided that there is some structure in the solution of a PDE. So for fluid flows, I've worked on this for many years. The structure comes from statistics. It does not come from the deterministic map. The deterministic map is very badly behaved. It's sort of, the trajectories are going to separate super exponentially. But statistically, this is a well-defined concept. So if you go from a probability distribution to the end probability distribution, there is no mathematical theorem which says that is the case. But empirically, we know for a fact that this is indeed the case. So what we can do is statistical computation. We can compute statistics. So we can directly go from here to here instead of going through this graph, right? So in other words, we can sample what is called a conditional distribution. Given an initial condition, I'm going to sample the trajectories of the potential solution. So this is the learning problem now. It's not the learning problem I started out with, because that is ill-defined. This is a well-defined learning problem. How can we do that? Well, these days, the most common way is to use what is called conditional sampling. So anyone who has used ChatGPT knows this. So if you give it a prompt, then it will provide you a nice picture like this, right? And the way it does it is by using, or many models do it, is by using what are called diffusion models, right? So diffusion models are a way in which you sample from a distribution, a conditional distribution, by sort of relating it to a target distribution. A known distribution. So this is your target distribution. Your known distribution is typically a Gaussian, noisy Gaussian, and what you do is twofold. So there is a forward step where you add noise, and a reverse step where you denoise. And in this denoising is where you can get these kind of nice pictures. So let me explain it how we can use this for our purposes. Okay. So what I'm going to do is that I want essentially, given some noise and given my initial conditions, I want to get my solution, right? So this is my objective. So first what I do is for my training data, so given this initial condition, given the solution at a later time, I add noise, okay, I add noise, I take it to something noisy, and then this can be done by a stochastic differential equation in practice. And this stochastic differential equation can be reversed. Here is the expression, you don't need to understand it, it's pretty complicated, but this is a straightforward way in which you can reverse the stochastic differential equation. And to reverse the stochastic differential equation, the drift term of the stochastic differential equation is given. What we do during training is essentially given initial condition, given a noisy sample, all that we do, and of course we know what is a clean sample, this is my ground truth, I just take out the noise, I just train it such that you recover this. So it's the same neural network, the neural network does not change as before, whatever I had, whatever, so it's still insensitive. But the process itself, the way I deploy it is that I don't directly infer from it. Instead, I use it as a term in a stochastic differential equation. So whatever small scale features I was losing by averaging things, I'm recovering them by adding noise. Okay, so this is sort of the delicate process, and in the paper we have even a proof that it recovers the right conditional distribution. But does it work? Very well, actually. So well that I will. So it works so well that as you can see here, so it's clear if I take the vorticity for instance. So this is what the traditional machine learning algorithm gave me. Everything was washed out, right? But now you can see that this is my ground truth. This is what my model, this GenCP, this diffusion model, this generative model gives. And these are very, very close to each other. The samples, you cannot distinguish them by eyeball, and particularly the statistics, because this is the variance. Remember that we are losing variance completely. This is zero. But now the variance is totally recovered. And you see that in all the metrics, you see it in the probability distribution. So now we are stopping this regression to the mean. So we are recovering all the small scales in the flow. And this is, I think, a very, very important point, right? Because now we are able to simulate these kind of very, very complex solutions of PDEs, but using the right kind of machine learning model. Because if you just use your standard machine learning model, this is what you get. So once we have it for a Cartesian grid, we can do complex grids. That is our complex flows. So here is an example. This is flow past essentially smoke from a chimney or flow from a jet engine nozzle. And you can see that before you were not getting the smoke, you were just getting the jet. But now, of course, we are able to recover the smoke, which is quite hard. Similarly, for atmospheric flows, for shock waves, and so on, you can really do this. And what is the advantage of doing this is that instead of taking 15 hours or 14 hours with my old finite difference code, this takes about 4 seconds. So in 4 seconds, you can simulate a complex atmospheric flow. And then this is even 1 or 2 seconds. 2 seconds, you can simulate this flow past coming out of an nozzle. So this is quite impressive in that sense. And what about the examples? The examples that I started out with, right? So actually these can be readily applied because all of this fit into the framework that I just described. So the tsunami simulation, earlier it used to take 1 hour, and 1 hour is too slow, right? Because this is actually the solution after 1 hour. So by 1 hour, the tsunami has hit all these points. So you cannot issue a evacuation warning. Now with this method, it takes about 1,000th of a second. So it's really fast because it's 2D, so it's extremely fast. And even my worst prediction, which is somewhere along the coast of Italy, is quite acceptable. So it's sort of this really worked well because we have a lot of data. For the race car, this is it's not possible to do it publicly, but I can show the slides. This is we are able to do this now. Earlier it used to take 20 hours to simulate flow past a race car, but now this can be done in 1/10 of a second to 1/100th of a second. So using the methods just described. So there is slowly there is this ability to solve complex problems, right? So I could say that, oh, machine learning is very successful and I can just stop here, but there is a catch. There's always a catch, right? So what is the catch? So these pictures, what they represent is all the models that I've spoken: the diffusion model, the transformer, the graph, the convolution, all of them. What they do is that they scale with data. What does it mean? That the error, which is on the test error, this is on the y-axis, and this is the number of training samples, the amount of data that I need to feed the model. So all of them, there's also some theory by us and by others, that as long as you add more data, you get better and better errors. Still you saturate. There's always a saturation regime here. But but this alpha, at best this is 0.5, half, because of central limit theorem. But it's usually in practice less than half. And what happens is that this means that you need a lot of data. So all the examples that I showed you, the regime was 1,000 to 10,000 samples. So someone has to give you 1,000 to 10,000 samples, data samples, and then you can make predictions. It's okay for climate because we have a lot of data for that. But in most engineering applications, to simulate 10,000 flows past a car shapes is just impractical, right? So machine learning works if you have data. But if you don't have data, or if you don't have sufficient amount of data, what do you do? So this is the challenge. Let me try to address it in the last roughly 10 minutes. 10, perfect. So 10 minutes is enough to describe that. So let's take inspiration from, I should have also put DeepSeek. I'm in China, but you know, any of these new models that are out there, this sort of agentic AI models. So these models, they're able to do this, right? So if you go to ChatGPT, you don't need to provide it any data. You need to provide it a few prompts and it gives you the answer, right? It's sort of, whether it's satisfactory or not is another matter. So it is able to somehow work with, at least at the level of deployment, with very, very little data, almost no data in some sense. All the data is in the form of the prompts. So how do these models do it? If we can do that, then our problem would be solved, right? So these models are what are at the base is what is called a foundation. So what do they do? A foundation model is essentially a machine learning model that has been trained on lots of different types of data. So for instance, for ChatGPT, this could be text and images, but text is not English and Chinese, but English, Chinese, Hindi, whatever, right? And similarly, it's not just scientific literature, it's novels, it's poetry, everything, internet scale. So it's a lot of diversity of data. This goes into the foundation model. The foundation model is trained, and then at deployment, you take any of these domains, you take the foundation model, you take some data from that particular task, and then you use that, right? And today, the large language models are so good that this is in the form of even prompts. So this is a very, very powerful sort of paradigm to do this. Now for PDEs, it turns out, or for physics in general, this is a very natural pipeline. Why is that? So think of different PDEs that we know. Let's say that this is Poisson, heat equation, wave equation, Navier-Stokes. So if you go this way, we have infinitely many, but not so many. So there are only so many PDEs that we know. But for each PDE, we have, so this can be different languages, for instance, right? We have only so many languages in the world. But for each of these PDEs, we have different operators because we can change the initial conditions, boundary conditions, whatever. So this is how it is, right? So now what a foundation model could do is it could take some PDEs, take some operators from these PDEs, get pre-trained, and then if you have a new PDE or a new operator from an existing PDE, it can be fine-tuned or it can be adapted. And the challenge would be, can we do this? Could use a lot of data because this is in our hands, hands of a big tech company usually. But the question is, can we do this with very, very few samples, right? So this is going to be the basic idea. Uh, Many of us teach PDEs or numerical methods for PDEs, and it seems to be an impossible thing to do. Why? Because when I teach PDEs to my undergraduate students, I start with the Poisson equation, then I teach heat equation, then I teach wave equation, then one nonlinear equation. They're all different techniques, there are all different ways to do it. Also for numerical simulations, one with finite elements, finite difference, finite volume. So there's no connection. They're like islands which are separated from each other. So a priori, this shouldn't work. That you can't really build models which can take information from different types of PDEs, for instance, right? But unless until we try it out, this will will never succeed. So the attempt in this direction is what is called Poseidon. This is a model that we have introduced. This is publicly available. You have the model, you have all the data, you can test the model. Everything is open here. So it's a foundation model because it has, first of all, the model itself is this operator transformer that I just described, but it could be something else. But it is an operator transformer. But now the data, right? So foundation model is all about data. It's not just about the model itself. So the data is this is a proof of concept. It's not full 3D with all the scales that I told you. So it is just two PDEs on the square. This is the incompressible Navier-Stokes equation, high Reynolds number, and the compressible Euler equations because with shock waves and so on. Two PDEs in the pre-training set, and this amounts to something like 5 million images. So this is not a huge data set, but it's pretty big for scientific computing purposes. The biggest model that we have released publicly is 630 million. We have a model that we have trained which is more than 1 billion, but we have not yet released it. It's still training, right? So this is your foundation model, but who cares about the model? What you really want is this specific downstream tasks where you can fine tune the model. And here we chose in the paper at least 15 tasks. Remember that it has been trained on Navier-Stokes and Euler. So some of these tasks are from Navier-Stokes and for Euler, but for different initial conditions, for instance, or boundary conditions. But now some of them here, for instance, the wave equation, this has not been a part of the pre-training set, the Poisson equation, Helmholtz equation, Alan Kahn, and so on. So there are different new physics, some existing physics, and so on. So it's a mix of different tasks, right? The main challenge is, can I take my model and make it understand new physics? This is sort of the key. Otherwise, this will not work. So how do I test it out? Means, okay, this is a detail I can avoid that. The way I test it out is in the following way. Okay, so I take a task, one of these learning tasks. I run my standard model. This could be FNO, for instance, which I described in the beginning. I see how much of error does it make with 1,000 samples, right? And then I take my foundation model or any model for that matter and see with how few samples you can get the same error. Because the challenge is that you can only have limited amounts of data. So if you, in this particular case, it's with 40 samples, you get the same error. So you get a factor of 25 as a gain, right? So that is the idea. Or you could fix the number of samples and say that how much of the error reduction it happens here. So here maybe it's a factor of 2. So this is the way in which I'm going to measure this. So again, there's a table, but let me go to this. So what does this two graphs here represent? So this represents the gain in sample efficiency on an average over these 15 tasks. So with my largest model, which is 630 million parameters, I say that I have a gain of 50, which means that earlier, if my machine learning model needed 1,000 samples, this foundation model, which has been trained on this large amounts of data, for this particular task will only require 20 samples. Okay, so essentially I can reduce the sample complexity quite a lot. These are the different models that I have. This model, this is from New York University, but this one is actually from Xinhua. So it's this is the second best. We are not the only people who are doing it. We are at the moment the best, and these I visited them. They also do very good work. You see, their model gives you a sample efficiency of approximately 30, which is also considerable. But there are some interesting things. So this is also the gain in error. So the gain in error is I fix the number of samples. Earlier I had 20% on an average. Now I'll get an average 2%. So this is the advantage. The advantage is that my models, they scale with respect to a bigger model does better, right? This is what you really like. Here, not so much, right? The bigger model was not giving better results. The second thing here is that even though my convolutional based approach and transformer based approach, when they are treated for a single task, they are pretty identical to each other. As foundation models, they are very different. So transformers are much better than a convolution based task. But these are some of the details. So this is very satisfactory. If I can do all my simulations with 20 samples, I'll be or 40 samples or even 100 samples, I'll be very, very happy, right? Because that would be quite an achievement. But this is still 2D, this is still small scale. So take it with a pinch of salt, right? It really needs to be scaled up. And now, just to finish, let me give you an example just to illustrate how this model works. This is just the Poisson equation. Very, very simple problem, right? So this is the forcing term, this is the solution. Just diffuse this out. But remember that from my model's perspective, this is a very, very hard problem. Why? My model was trained on fluid dynamics equations. It was trained on time-dependent problems. It had periodic boundary conditions, right? This problem is an elliptic problem. It has no time dependency whatsoever, steady state, and my input-output relationship is very, very different. It's from a forcing term to the solution, not from an initial condition to a final condition, and it also has Dirichlet boundary conditions and not periodic boundary conditions. So from my model's perspective, this is new physics. It has never seen this physics, right? So the question is, how does it work? Actually, it works very well. So this is when I use my model. This is when I just use a very small part of it. Only the I freeze the latent direction. Let's focus on this one. So remember that my input is like my input is this. So it has been trained on fluid flows. So it should interpret this as the initial condition of a fluid flow and try to flow these vortices around in some sense, right? But even with one sample, it doesn't do that. What it does instead is that it more or less returns back the initial condition, realizes that something is wrong, returns back the initial condition, and just sort of moves it around a little bit. With 16 samples, it is learning diffusion, right? So it is, you see that it is sort of diffusing out. It's not accurate, but at least the physical process is correct. By 128 samples, it learns it perfectly. So actually, it has learned some physics in the fluid flows that it is able to take to the Poisson equation. Otherwise, with one sample, it wouldn't be able to, or 16 samples, it wouldn't be able to do what I want to do. So here is it in action. The model itself is very, very fast, but again, I'm out of time. But the main point that I want to make is that this picture that I gave you with different islands, perhaps this is not correct, because otherwise the model won't work. Instead, what it is probably leveraging, we don't know it yet, are hidden relationships between different PDEs that you can take information from Euler and Navier-Stokes, go to Poisson equation, go to Allen-Kahn equation, and so on. And if that is the case, and if it holds in 3D with complex domains and so on, then we can really deploy these kind of foundation models. So yeah, so I'm almost finished. Almost. It's all. This is my last slide. So what we're doing now is that we are just taking it up to 3D, to adding all these unstructured point clouds and so on. So this will hopefully come out later this year. And now I conclude. I'm totally out of time. So what I want to say is that to let's say emulate traditional numerical methods for PDEs with machine learning is getting more and more feasible. I described different methods. Particularly important is when you go to 3D, arbitrary domains, and when you work with multi-scale chaotic PDEs, then you need different structures, different constructs. But all the time, data is the challenge. If you don't have enough data, you are this is not going to work out. So you need data, right? And the way in which you can leverage data is through these foundation models, if we are able to scale them up. But this is still an open question. So with that, I stop, and thank you very much for your attention.
Thank you, Professor Mishra, for this intriguing talk. Any questions from the audience?
Yes. Yes.
But when you build this current model, you talk about the input.
Mhm.
So what type of data? Just like directly use imaging, or you use some of
No, just simulations. It is completely based on simulation data. I actually had a slide.
so you're using some of code.
Yes,
So
my own.
a lot of some.
Yeah, yeah, this is my mom, our own codes, right? So this is sort of, all of this data is generated by pretty standard numerical methods. It's not something fancy, this is sort of pretty standard numeric, something on spectral methods, some with finite volume, some with finite elements. So it's all simulated data at the moment. We have access to some experimental data, but this is not in the paper. This will be in the next next paper. Yes, lot. Right, there's a lot of there's. Mm. Yes, yes, billion. Yeah, we need a lot of compute. We have access to quite this is one advantage being in Switzerland, that they have invested in a very powerful supercomputer. We have access to quite a bit of compute. But I expect in the next release, we expect a 2.5 billion parameter model. And then maybe in a couple of years, we will come up with a 10 billion parameter model. But I think that's what we can afford in academia. We cannot afford chat GPT level with trillions of parameters. This is not beyond our control. But I think 10 billion we can manage. So I also work, I didn't talk about it, but I work on foundation models for climate. Because then there's more funding, right? This who is willing to fund for PDE research, but for climate there's a lot more funding. There we are even funded for 20, 30, 40 billion parameter model. But climate has a lot more data, so a lot more data which is available. So you can. So the challenge is not the model size; it's the data, because the data has to be sufficiently large for a model to. Yes, that is really the challenge. Even for a foundation model, you need to generate a lot of data. That's the challenge. But it's a good question. It's a relevant question. Yes.
So several quick questions. So first, so in your foundation model, is it
No. It is, maybe you can interpret it as a dictionary, but I don't think it's per se a dictionary. It's more like a mixture probably, but it's sort of it's difficult to classify it in a clear way. But I sort of see the question why you ask, but I wouldn't interpret it, because to be honest, I really don't know if it is acting more like a dictionary. I think it's more like a mixture of data mixture. That's the way I interpret it.
mixture? So can you can you do fine tune based?
Can I do
fine tune?
fine?
Can you do fine tune based on?
Yes, all of this is found. So all these tasks that I'm telling you are fine tuning tasks.
Okay.
So
okay, you have listed
yes.
so many equations
Yeah.
in your model,
Mhm.
in your foundation model, but if one step forward we have another equation, there should be some structural difference.
There could be some structural differences, but this is what I am pretty confident that the model can handle, right? Of course, can it handle everything? The answer is no. But this equation, as I was telling my colleagues just now, this has very different structure from the structure of the pre-training data set. But of course, without fine tuning, this will not work, right? Because it's not a zero shot model at all. It doesn't work zero shot, but it's a fine tuning model, and the only reason why it could work is because physics itself, or PDEs at least, they are not totally unrelated from each other. There is some information transfer, there is some connection between different PDEs, so that the fine tuning can leverage it. Because otherwise, there's no chance. So if you take some completely random PDE with completely random behavior, of course, this model is not going to work on that. So
last question.
Yes.
Can you explain a little bit how you add back the small scales?
Oh yes, this is a good question. This was with the diffusion models, right? So no, I went the other way around. Maybe I'll do it quickly and then go to the next topic. Slow. Yeah. So this is the relevant slide, right? So the small scales are not added by me manually or anything, right? This is a consequence of the diffusion model. So remember, what does the diffusion model do? The diffusion model, it solves this reverse. So give at inference, what happens to the diffusion model is, given the initial condition, for instance, or a previous time step, and given noise, you solve this stochastic equation, right? And when you solve the stochastic differential equation, at each step of the stochastic, so now just imagine that Euler-Maruyama discretization, Euler discretization of this stochastic differential equation. So at each step, it takes this guy is here, and it starts denoising it a little bit, right? So it just starts denoising it a little bit. So this has a lot of small scale structure because it's noise. There is nothing wrong with that. So it takes noise, and then this map probably is insensitive. So you might not, in the beginning, you don't have a lot of small scale structure. I have even a figure somewhere in the paper, but you don't have a lot of small scale structure. But as you put it into the stochastic differential equation, you sort of take out the noise is somehow induced from the process itself, from the diffusion process itself. It's not coming from the model. The model is actually taking out noise. It's the noise comes from the fact that we are solving this ST iteratively. So this is roughly intuitively what is happening. So whatever I am cleaning out, because it's an iterative process. If I only use one step, this will not work, right? Because I use many steps. Actually, not that many. With 16 steps, this is good enough. But if I have, say, many steps, each step, the noisy process of the stochastic differential equation itself is keeping my. I have some very nice one-dimensional examples. I don't have them here, but if you're interested, I can send them to you, where this is beautifully illustrated how it works in 1D, how it sort of because the way the diffusion model works is that it never it starts with a very it tries to remove noise, so whereas a machine learning model, it first learns the low frequencies and then starts adding the high frequency. Here it takes the full noisy thing and starts removing noise, and then you get this. But I if maybe if you have 1 minute, I can show it to you also. There is a very nice picture where I can show this, but I didn't have it on my slides.
Considering the time schedule, maybe we need to stop here and let's thank the speaker again.
Thank you very much.